Hello students, up to now we have discussed what is group, what is a subgroup, what is left coset, what is right coset. Now it is the time to find a new subgroup which is a combination for all these uh, group and subgroups. So let's find a new subgroup, normal subgroup or invariant subgroup, or it is called self conjugate subgroup. So for any subset to be a normal subgroup, it must be number one, it must be non-empty, it must be subgroup, and then it will be normal. So any non-empty subset of a group to have a to be a normal subgroup, it must be non-empty, it must be a subgroup, and third it must be normal. So let me define what is a normal subgroup. Let H be a subset of a subgroup of a group G. Let's be a so if it is a subgroup of a group G, so it's first it is a subset, then it is a subset of group G, then it is a group in itself. Any subset of a group G is a subgroup if it satisfies all the four axioms of under the same binary composition. So let H be a subgroup of group G, then H is called a self-conjugate or normal subgroup of G if every left coset of H in G is equal to the corresponding right coset of H in G. So we have read about the what is left coset and what is right coset in the definition of. So that is what is the meaning of this? This means suppose A belongs to G, HA is called the set of HA where H belongs to H, set of H, small h into A belongs to H belongs to small h into H, and A belongs to G is called left coset, and set of small h into A, HA is equal to H is the set of all small h into A, such that for all A H belongs to H and A belongs to G. So any subgroup of a group G is normal if the left coset of H in G is equal to the right coset of G. If the binary composition is multiplication, so this is this. If the binary composition is addition, then A plus H is equal to H plus A for all A mod H. Now another definition. The definition based on the left and right coset. Now another definition of the normal subgroup or related group is if H is a subgroup of a group G, then H is called a normal subgroup of G if for all X belongs to G and for all H belongs to H, X inverse belongs to H. X inverse X inverse belongs to H. This is another definition of the normal subgroup. Now, some important facts. When G is an abelian group, then every subgroup subgroup H of G is a normal subgroup. When G is a abelian group, then every subgroup H of a group G is normal subgroup. For that is H is equal to H H. H is equal to H for all E belongs to G. Next is the subgroups E and G of any group G are always normal subgroups. The set consisting of the single identity element and the group itself are always normal subgroups. These normal subgroups are called trivial normal subgroups. So we don't discuss in the preceding lectures that we'll discuss the proper subgroup of a group G. We'll show the proper subgroup of G which is to be normal because every set consists of identity elements. Set consists all the elements of G. They act as a normal subgroups. So it is noted that H is a normal subgroup of G. This is notation for this. If H is normal subgroup G, it's noted by this H triangle G. Now, what is Hamiltonian group? An non-abelian group non-abelian group, each of whose subgroup is normal. It's called Hamiltonian group. And non-abelian group, each of whose subgroups is normal. It's called Hamiltonian group. Now, let's prove. The first thing based on it, a subgroup H of a group G is normal subgroup of G if and only if G small h G inverse belongs to H. For every small h belongs to H and G belongs to G. What does he say? He says that a subgroup H of group G is normal subgroup of G if G H G inverse belongs to H for every H belongs to small h belongs to H and G belongs to G. The necessary part, this is subject part. So we are talking necessary part. This is called necessary part, if part, or if part, if part. So we'll suppose assume that let given this let H given is let H be a normal subgroup of G. Let's say normal subgroup G. Uh, what to prove? We have to prove if H is normal subgroup of G, let H be a normal subgroup of G. And if in the definition by definition, therefore GH is equal to HG for all G belongs to G. Definition also in quotient form. Now what to prove? Our needs to prove G H G inverse belongs to H for small h belongs to H and G belongs to G. So now we'll start from here. Given is this GH is equal to HG, GH. We'll take an element from G belong to GH. So let H belongs to H and G belongs to G be any element. When element we are taking element from GH. Then GH belongs to GH belongs to GH. This GH belongs to GH, but the GH is equal to how much? Given is as a normal, the GH is equal to HG. So this GH also belongs to HG. If GH belongs to HG, then GH must be of type H1G for some H belongs to H. For some H belongs to H. So since because H is subgroup in itself, and we have read in the properties that if H subgroup, then cancellation law, both the cancellation law hold true in H. So apply cancellation law, right cancellation law by G inverse. So if we apply right cancellation law, J is equal to, what will this become? G H G inverse is equal to H1 G G inverse. G G inverse is equal to E. G equal to G G group. G G inverse is equal to E. Inverse of every element in G like this. And H into E, H is subgroup. So H into E is equal to H1 into E is equal to H1. So this implies G H G inverse become equal to H1. So H1 is the element of H. This implies G H inverse belongs to H. Now sufficient part or if only if part. Now what is given? Given is H is a subgroup of group G and G H G inverse belongs to H. For all H belongs to H and G belongs to G. I was able to show H is a normal subgroup of G. H is a normal subgroup of G. What to prove then? I will prove that AH is equal to HA for all H belongs to G. So in order to prove HA is equal to AH, we have to prove the two parts. HA is subset of AH, AH is subset of HA, and HA is subset of AH. Two parts. If AH is subset of HA and HA is subset, then they are equal. So the first part, let A belongs to G, be an element. And given is if you belongs to G element, therefore A H inverse belongs to G for all H belongs to H. This is given. Given prove is AH is a subset of HA. So now take element A from AH. Let AH belongs to AH for all H belongs to H. Any element. Any element. Then AH can be written as H into E. H into E is equal to Z element of this H subgroup. G and H G subgroup and this not 3 and A into H into E. So E can be written as A into A inverse is equal to A inverse into A is equal to E. Is equal to E. So this, what will this become? This become equal to A asciotic holds in a group A H A inverse into A. So A, we are given that A H inverse belongs to H. Therefore, A H inverse into A belongs to AH. So we assume that AH belongs to AH belongs to AH, and prove that AH belongs to HA. Belongs to HA. So this first implies AH subset of HA. Now second part, HA is subset of, we have to prove HA is subset of AH. So let B is equal to inverse. We have to apply, so we have to follow some certain technique to prove these, and we are doing all the four exams, and we are using techniques only. Let B is equal to A inverse be any element of G. Therefore, B H B inverse also belongs to H. For H means this is given. B, if B is an element of G and B is equal to inverse, then therefore B H B inverse also belongs to H. For H means this is given to us. Now substitute the value of A from here is equal to, but B H B inverse is equal to A inverse H E inverse of A. This become A inverse H A. A inverse H A belongs to H. A inverse A belongs to H. So this becomes, what this become? This will be inverse B. This belongs to H. This belongs to H. Therefore, we substitute the value. So we come to the conclusion that A inverse H A belongs to H. So now we use this later on. Let HA belongs to H. This let again. Let HA belongs to HA. Any element. HA can return E into HA. It's written as, we have proved this. You in order to, you will use this here. So this is equal to HA is equal to E into HA. E is equal to A into inverse into HA. So a Shitula holds G group. This is equal to A into A inverse HA. Now A inverse HA, A inverse HA belongs to H. So this belongs to A into H. So we have shown that HA belongs to H and shown that HA belongs to AH. We have taken that HA belongs to HA and shown that HA belongs to AH. HA belongs to AH. HA belongs to AH. This belongs to AH. This is not here. This belongs to AH. So implies, third, fourth implies H is equal to this. So now A and B implies H is equal to H. H is a normal subgroup. Now let's submit. Uh, let H be a subgroup of group G. If H is a normal subgroup of G, then the following statements holds true. Argument. If H is subgroup of G, if H is normal subgroup of G, then the following statements are true. That is, first implies second, second implies third, third implies first. Then next H is normal subgroup of G, then G small h G inverse H for all even H for G belongs to G and H belongs to H implies G capital H inverse H for all G and G H is equal to G for all. So now first implies second. First implies second. Let's assume that first H in normal subgroup G. Given is H in normal subgroup G. H is a normal subgroup of G and G small h G inverse belongs to H for all G belongs to G and to prove, G H G inverse is equal to H for all G inverse. Now, since G H G inverse is H is given, G inverse H for all G inverse G and G. So G H G, if G H G inverse H, so it will be of the type, it will be of type H1 for H inverse H. So if G H G inverse is equal to H1 for some H inverse H implies H implies GH. For different element of H, they, for this is for some H, it lies. This holds true for all elements of H. G H G inverse is equal to H for all G one of G. The second part, since G H G inverse is equal to H for all G one to G, this applies. Apply right constitution law by G. Yes. G H G inverse into G G H. G inverse is equal to E, so G H become equal to G H equal to H. Is equal to E, E into H equal to this, so H G H equal to H. Imply third. Third implies first. Since G H is equal to H for all G belongs to G, so they are the subgroups equal to this. So if they are equal there, then this is equal to G H is equal to H1G for H and G belongs to. Then G H is equal to H1G, H1G for some H and G belongs to H. Now again apply left right constitution over G inverse because G and H is equal G and H is group and H subgroup. G H G inverse is equal to H1 G G inverse. So this will become G H G inverse is equal to H1. Okay. This is like G H G inverse. So you have to note on this stuff. It will get a problem for you. So why, how this is possible? So they must be, that must be equal. Equal, but this is not true here in right hand process. It's not always, the groups are not always complicated. First, the second, second, the third, and third, the first, and hence the all the three statements are equal. The third term is a subgroup H of a group G is a normal subgroup of G if and only if the product of two right coset of H in G is a right coset. A subgroup H of group G is normal subgroup if and only if the product of two right cosets G is right coset. Now necessary part. Looking at necessary part or if part. Let H is let H is a normal subgroup of G, and let H and H be any two right coset of H in G for all A belongs to G. Now H into HB is equal to HA into HB. So H is normal subgroup, so HA is equal to H. H is equal to HA. So H law holds. So HA into HB can represent H into AH into B. AH is equal to H normal. So H is equal to HA. And now associated of H into H is equal to H. H normal subgroup. H into H is equal to H subgroup. H subgroup. Therefore H into H is equal to H. H normal subgroup. H into H is equal to H. A into B. H into A. Now since A and B belongs to G and G is a group, therefore A B also belongs to G. This is property. Therefore HAB is also a right coset of H. So the product of right cosets of H and G is a product of right cosets of H and G is the right coset of H and G. Necessary exception part. Given product of two right cosets of H and G is the right coset of H. What to prove? How are to prove? H is normal subgroup. So let X belongs to G be any element of G, then its inverse also belongs to, because H is a group. Let X belongs to G be any element of G, then X inverse also belongs to G because G is a group. And HX and HX inverse are two right cosets of the G. G. Thus HX and HX inverse is also a right coset of the G given. That's right coset G. That is HX inverse is equal to H HX HX inverse HX inverse is equal to H into is equal to H given. So this is a right coset is equal to HX inverse is equal to H. For E belongs to H, E into X belongs to E into X belongs to H into X. and E into X inverse belongs to HX inverse. So EX into EX inverse belongs to HX to HX inverse. EX into EX inverse is equal to, comes out to be E, comes out to be E. So E belongs to HX and HX inverse. Also E belongs to H, E belongs to HX and HX inverse, and E also belongs to H. Thus, H and HX inverse are two right cosets having one element common. Right? So E belongs to H and E belongs to HX inverse. So this shows that H and HX inverse are two right cosets having two elements common. Also, we know that two right cosets are either disjoint or identical. Disjoint or identical. Therefore, they have one element common, so they are not disjoint. Therefore, uh, they are identical. Means H is equal to HX inverse. H is equal to HX inverse. Now let HX small H1 X inverse belongs to HX inverse. For all H and H1 belong to H and H belongs to H. Using that method. Therefore, Hx H1 and X inverse belongs to H. For all H1 H1 belongs to H and G belongs to, because H is equal to HX inverse belongs to H. Now applying the left cancellation law by H inverse. H inverse. So if you an associative law, so H inverse H X H1 X inverse belongs to H inverse X. So H inverse H is equal to E. So this become equal to X H1 X inverse belongs to H1 H. H is subgroup and H belongs to H and HX equal to H. So H is equal to the subgroup X belongs to H, then HX XX belongs to H is equal to H. So XX is equal to H. This implies X H1 where X inverse belongs to H for all H belongs to H in this implies H is a normal. Next remains prove that intersection of two normal subgroups is a normal subgroup. Prove that intersection of two normal subgroups is a normal subgroup. Let H and K given is let H and K be two normal subgroup of group G. Therefore, H and K are subgroups. If they are normal, first they must be subgroup. So H and K are subgroup of G. If they are subgroup G, we also know that intersection of two subgroups of a group G is again a subgroup. So if H and K are subgroup, then H in we proved this theorem in the previous lecture implies H intersection K is also subgroup of G. Also subgroup. Let X belongs to G and H belongs to the intersection. Be any element. The element. Since H belongs to H intersection K, this implies definition of intersection. H belongs to H and H belongs to K. Since H is a normal subgroup G, therefore X belongs to G, X belongs to H is normal subgroup G. Therefore, X belongs to G, H belongs to H, then X inverse belongs to H. This is given. H and K are normal subgroup. This is a normal subgroup. Now, similarly, K is also a subgroup of G. So X belongs to G, H belongs to H, and X inverse belongs to K. Implies this both first implies X inverse belongs to H and X inverse belongs to K. It implies they common in both. So X inverse belongs to H intersection K. Thus, X inverse belongs to H intersection K for all X belongs to H and K belongs to H intersection K. Guys, H intersection K is a normal subgroup of G. Next image. Prove that intersection of any collection of normal subgroups of a group is itself a normal subgroup. Intersection of any collection of normal subgroup of a group is a just a normal subgroup, just self a normal subgroup. So given let G is a group and H lambda, so lambda belongs to capital lambda, any number, be any family of normal subgroup G, be any family of, we don't know how many numbers are there, but as as many elements, as many they are all normal and they sub the normal subgroup G. We don't know the number, how many they are number. So whatever number there may be, and let us suppose that n is the intersection of these h lambda normal subgroup G, the lambda belongs to lambda. Okay, like this. Now lambda belongs to lambda be the intersection of this family of normal subgroups. Now what to prove? We are going to prove n is a normal subgroup. Is a normal subgroup. Again, you have to show the normal. So we have to show first it is a subgroup, it's non-empty, it is subgroup, and then we have to show it is a normal. Therefore, N is a subgroup of a group G. Why? Every normal subgroup of every normal subgroup is a subgroup of G. Any intersection of subgroups is a subgroup. And it's a subgroup. Every normal subgroup is a subgroup of G. So therefore, N is a subgroup of group G. Now our aim is to show that this subgroup N of a group G is a normal subgroup. So this is a normal subgroup and is a normal subgroup. So let us take any element and n belongs to n. Belongs to n means n belongs to the intersection of h lambda normal subgroups where lambda belongs to capital lambda, and x belongs to be any element, any element from belongs to this and to this. This implies if n belongs to capital N, then L belongs to the intersection of h lambda, lambda for all lambda. This means this n belongs to each of the h lambda. If h belongs to, if this n belongs to, the intersection means n belongs to each of this h lambda. Lambda belongs to capital N. Implies n belongs to h lambda for all lambda velocities. Each going to each h lambda, each normal subgroup h1, h2, h3, so on, whatever. Since h lambda is a normal subgroup of G, h lambda is normal subgroup G, therefore for all x belongs to G and h belongs to h lambda, implies n belongs to lambda, implies x and x inverse also belongs to h lambda. X, therefore for all x belongs to this and n belongs to h lambda, implies because this is h lambda is normal subgroup. That is normal subgroup. X and x inverse belongs to h lambda. Thus we have x belongs to G and n belongs to the intersection of h lambda, lambda belongs to capital lambda. This implies x and x inverse also belongs to x because it belongs to lambda for all lambda, every lambda. So this, if this belongs to this and this belongs to lambda, then this belongs to intersection of h lambda, lambda to this. So x and x inverse belongs to h lambda for all lambda belongs to lambda, implies intersection of normal subgroups is a normal subgroup. Thank you very much. Thank you very much.